Welcome back. I'm going to do simulation tutorial number 1, static stress analysis. The point of this lab is to give you a basic exposure to stress analysis. Stress analysis is a pretty complicated subject, and there's a lot of courses you'd have to take before you could really understand what they're talking about. But the basic idea is when you pull on something or push on something, that is, when you apply a force to something, it's going to move a little bit. So we call that the strain or the displacement. And that force will also result in stress. And there's a certain stress at which a part will break. So if the calculated stress ends up being the same as the yield stress of the part, it'll break. Another way to say that is the part would have a safety factor of 1, which means that you apply a force, you get a certain stress, and that stress is right at the breaking point of the part. So it has a safety factor of 1. It's just barely strong enough. We want more than that. So 2 would be pretty good. A safety factor of 2 means that the part is twice as strong as it needs to be. So something like an airplane, you want to keep the parts light, so you might have a stress factor, a safety factor of 2 or 3, meaning the part's like 2 or 3 times stronger than it needs to be. Something like a bridge, it doesn't have to be light, and you want to make really sure that it doesn't break, so you give it a higher safety factor, like 5 or 10. So that's the basic idea. Now this lab, you got to be really careful that you set everything properly, otherwise the analysis will fail. I think, for me, I had some trouble with the getting the units to work right. All right, I'll just get started on this. So I have Fusion up. We are going to need to save this, so it's good to make a new project folder. I called it SimToots. Now get into basic training, get into simulation, open this connecting rod assembly, go up to File, Save As, and I want to make a new folder, so I'll click this down arrow and get into SimToots and click New Folder. Not that I really need a folder, but that's what they ask you to do. I'll get into that. So I'm storing this project called Connecting Rod Assembly. I'm putting it in the SimToots folder, in the Sim folder, in the SimToots folder. Anyway, it's saved somewhere. So there's that. We'll close this data browser thing. So I forgot to say, you need to make sure that in preferences here that you have this Z up. Now you have to set Z up and then start a new project, right? That's the way that thing works, is you set Z up and then start a new project, and then get into that project and make sure it's Z up. You can't change it in the middle. You have to change it before you open the project. Okay, there's that. Then I think there's some problems with the units here. The default that it brings it in, for me anyway, was millimeters, and I think you have to change it here, although they don't tell you to do that. So change it there. Then we can start our simulation. So click on this big old button where it says Design and change it to Simulation. This thing pops up. Now you want to click right here on this barely noticeable little icon right here. Click that thing, go to Mesh, click Absolute Size, and here, be careful, 0.125 IN for inch. I have a feeling that I did this wrong, and I think it did millimeters. Basically what that would mean is that the number of squares, if I used millimeters instead of inch, the number of squares would be huge, and the study would take forever to complete. Okay, so be careful on that. Your study should complete in 5 minutes. If it doesn't complete in 5 minutes, maybe 10 if your computer's slow, it's not right. Okay, there's something wrong, all right? So set that to 0.125, make sure there's IN in there. Then you click back and then create study. And I'm paranoid, so I'll go up here to settings and click that and go to mesh and make sure, see, it changed it. What's up with that? I don't understand. Let me cancel. Let me go back to my, that's it. That's it. You got to go into this thing. Yes. So you set the units before you start the simulation. Then after you start the simulation, change these units again to inches. Okay, so just make sure that your units are in inches like everywhere. And then go back to manage, settings, mesh, 0.125 inch. Click OK. I'm going to go back in one more time. Mesh, 0.125. That's okay. Then this thing, inch. All right, great. And I remember I set up inch in the original model before I even started the simulation. Okay, I think that's where I went wrong. Maybe I'm spending too much time on that, but it was very aggravating. Okay, then they ask you to get in here to materials, study materials, and check that you can get these to expand if you select this first, and then you can drag this over. Make sure that these are the correct materials, and they are. But look at this thing right here. If you click this properties thing, you see this. You see the yield strength, 37,000 psi. So if the calculated stress gets to 37,710 psi, that means the safety factor would be 1 and the part would break. If the yield strength gets to half this value, that'd be about what, 18,000 something? That means you have a safety factor of 2. We're going to end up with a safety factor of 1.5, 1.7, something like that. All right, so we'll close that. We have to apply a bunch of constraints now. So you go up to constraints, structural constraints. The first one, you're going to pick, let me cancel this target out of here. You're going to pick this, and then the bottom of that, and all your XYZ constraints are on. So this thing's really fully constrained, basically. And say OK. Then get into your the model components. Open up this junk. Turn off the connecting rod visibility so that you can select some more stuff. And go structural constraints. This time we want just the Z-axis. Click this line and this line and this line and this line. So we're constraining this big cylinder so that it can't move in the Z direction. And we click OK. Then you can right click and do repeat structural restraints, or if you want, you could just keep going back up here, structural constraints. We want just the Y axis, and we want this ring, that, all the circle, this edge, these edges down in here. So now we're constraining this cylinder in the Y direction, so it can't slide slide in its hole there in the Y direction, which I guess is up. Although let me check something here. Click OK. I'm going to go back to my preferences real quick. Yeah, you need Z up. Yeah, that's correct. It's just confusing because even though Z is up, Z is pointing towards the front view, not the top view. Anyway, that's good. Let's see, another constraint. we need to put on the connecting rod. So turn the visibility of the connecting rod on and turn the visibility of the large pin off. Go to constraints, structural constraints. This one's going to be just in the Y direction. And pick this edge and click OK. Those are all the constraints. So constraints basically determine which way the part is free to move, and right now it's free to move in the negative X direction mostly. So we need to put a force on it. Let's turn the pin back on. So we'll go to loads, structural loads. We'll select this face and this face and XYZ vector. I think the units, it's important that you leave the units in there, I think. So minus 2,000 pounds force, and click OK. We've got forces on there. Then we need to go to this contacts panel, click automatic contacts and generate. So that generated a set of contacts that specify how these parts can slide past each other or not. And this pre-check is green, saying everything that's cool is good with those contacts. But the tutorial tells you to change them. And so we go to manage, no, we go to contact, manage contacts. And these are all bonded contacts, which basically means they're stuck together. So click the first row, hold shift, click the last row, that'll select all of them. Click this drop down. So separation means they can move around, means they're not connected to each other at all. They could slide up and down and around, and sliding means they can only slide. I'm not sure what rough means, but anyway, change it to separated. Once again, the point of this is just to give you some exposure to stress analysis. It's not to master all these the physics concepts and the material science concepts. It's just to learn how to work this tool and say okay. Then if you click the pre-check, it tells you there's some warnings, and the tutorial explains that those are okay and it works. Those aren't the problem. I think the main problem I was having was with my units. Make sure it's inches. Make sure it's 0.125 inch. Say OK. Then you can click solve. This dialog comes up. You have a choice to solve it on the cloud. So it'll use some computer processing power somewhere over at Autodesk somewhere, or you can solve it locally. Now, I have a pretty fast machine. It solves it locally in about 3 minutes. Don't imagine most machines would take more than 10, but you can solve it on the cloud, and it uses up cloud credits. Eventually you might have to buy more. I don't know if they're going to enforce that or not, but I've been running it locally. So I'm going to hit solve, and it's running locally. Okay, this will take about 3 minutes, so I'll pause the video and start it up again when it's done. Okay, it's done. It says I have a safety factor of 1.74, and you can close that. You can go to this drop down here by this is a legend here, this color coded bar thing. We call it a legend, and you can go to stress, and then the maximum stress is 21,667 at this point. And if you remember, the material steel has a yield stress of 37,000. So the ratio of 37,000 to 21,000 is about what the safety factor is, 1.74. So that works, or makes sense. Let's see, there's stress, and then there's displacement, or how much this thing is moving. So it looks like it's moving 0.003 inches when you put 2,000 pounds on it. So it's moving 3,000ths of an inch when you push on it with a ton. So it's pretty strong. So that's that. Some other cool stuff you can do. You can go up to Result Tool and click Animate and push this little button, and it does this kind of cool thing, kind of nifty. Okay, and you can also go up to, the tutorial wants you to go to Compare and click the Compare button. Oh no, wait. There's nothing to compare it to right now. I need to run a second study. So right click on this first study and click Clone Study. It busts you out of the results mode and dumps you back to this simulation mode, and we're in study 2. It's active. The one that we just did, study 1, is up above that in the browser. So now we're doing study 2. So we're going to change how this little cylinder is constrained. So get into study 2 in the browser, expand the case load, expand loads, expand constraints. Constraint 1, the first one we added, is this first little cylinder where we constrained it in all 3 directions, so it's fully fixed. And right click fixed one and press delete. So there's nothing holding this small pin down at all, and when you apply this 2,000 pound force, this whole thing will just shoot off to the left and start accelerating at F equals ma, so divide by the mass, and that's the acceleration of this thing. It's going to just take off, so we need to put a force on this small pin to balance it out. So we go to Loads, Structural Loads, and click the top and the bottom. This is similar to what we did on the big pin. And then click Vectors, type in 2,000, so it's positive 2,000 now, and click OK. So we have a 2,000 pound force pushing in the negative X direction, another one pushing in the positive X direction, so those balance, and then the rest of the parts are constrained to keep them from moving in the Y direction and the Z direction. The tutorial now asks you to go up to this pre-check and observe that you have warnings, which don't matter. So we're ready to solve. I think our contact set is, you manage contacts. It's still separation. It's still what it was before. Anyway, we're ready to solve. So we click Solve, Solve. I'm going to solve locally. It takes about 3 minutes on my machine. So I press Solve. It's cranking away. All 4 cores on my machine are cranking away at 60-some%. I'll pause the video and come back when it's done. Okay, it's done. It comes up with this little dialog here that has the safety factor on there. So this one's got 1.56, a little bit less safety factor than the other one. You can close that, and you can get into this drop down and check stress and check displacement. And the other thing you can do is you can go to this compare menu and click compare, and it sets them up side by side. And you can go to synchronize and synchronize the camera and synchronize the result type. And then when you change the results, they change on both of these views. And when you oh, the camera's not synced. You see synchronized camera. Oh, guess you can't change that both at the same time. Odd. Anyway, all right. So safety factor is 1.55 on. Oh, the other thing is, let's see, down in here there's a drop down. You want to put model 1 on the first window, and then on the other, and then click on the other half of the canvas, and there's a drop down. Make sure it's on study 2. Okay, then you can, let's see, safety factor on this one's 174, and on the other one it's 155, and the stress is 21,666, the max stress. On this one, it's no, they're not synchronized. Synchronized result type. Stress. It's 24,000 versus 21,000. Displacement is 0.034 versus 0.0021. Anyway, that's basis of stress analysis. It's more important, the more you're trying to optimize a design, the more important it is. Like aircraft are highly optimized. You want an airplane to be strong enough and not a whole lot stronger than it needs to be, because that just adds weight. So safety factors are, 1 point something, maybe 2. It depends. Like if it's the wing spar, you don't want the wing to break off, so that you might have a little bit higher safety factor. But anyway, a lot of times you just make the part really big. Honestly, it's like I say, aerospace is when it's worth it to spend the time. But a lot of other industries, it's cheaper to just use more material than it is to pay somebody to do the stress analysis. Even if with these powerful tools. But it just depends. Anyway, it's a really important skill set to know about. Okay, so I hope this video was useful to you. I'll see you next time. Thanks.